We're very happy to have Melissa Zhang speaking about an annular filtration on Sarkar-Seed-Szabó's spectral sequence. So take it away.
All right, thanks, Catherine. Yeah, so first of all, it's pretty cool to be able to speak here because I think this crowd is very related to all the motivations of what Lynn and I did in this project, but also what we did is maybe on the day-to-day scale different from what most of you think about. It's somehow less geometric, more algebraic and combinatorial. So my goal for today is going to be slightly different from what I usually do with this talk. Instead of telling you about the applications and motivations from low-dimensional topology, which is part of the reason why I started working on this, I'm actually going to start with some of the cool constructions. And from there, hopefully, you'll see how this can relate to your work. And then I'll eventually end up talking about the properties of this invariant that we're going to define for anybody who's interested in that. Okay, so first of all, let me start with just an outline so you know where this is going. My first topic is that I want to tell you a little bit about Pavano homology, which is a link homology theory that comes from really representation theory. But it has a lot of relationships to geometric invariants, namely a lot of spectral sequences to Hager-Floer homologies. And a lot of the times you can sort of look at one side and think about what should be true on the other side. So the first thing is Pavano homology and its relationship to geometric invariants. Oh, I should say this is joint with Lin Trong, who I have seen is also here today. Okay. The second thing is then we have to move on to sort of, there's going to be a more complicated spectral sequence that is still sort of combinatorial in the sense that it's extremely algorithmic. There's not really sort of some geometry that you have to play with. You could just know the information and compute it. And that's called Szabó's geometric spectral sequence. And then the main construction that's relevant here is actually Sarkar-Seed-Szabó's perturbation of this. And by the way, I'm probably going to end up writing SSS for this. So really in this section, I want to talk to you about the symplectic version of Pavano homology defined by Seidel-Smith, because that was sort of the motivation for coming up with this combinatorial combined theory, which I'll tell you about. The third section, I'm not sure if everyone's familiar with this, so I just wanted to talk about these filtration defined invariants. So I will briefly talk about how you construct things like Rasmussen's S invariant. And this is a smooth invariant of knots in the three sphere, but it's functorial, so it's sort of, you can talk about sort of movies of knots and then how the S changes. And this takes us to upsilon-like invariants. And upsilon is an invariant coming from knot-Floer homology that basically says if you have more than one grading, you can sort of mix them together and come up with a generalized version of Rasmussen's invariant, or that type of invariant. And then I'll also talk about DT, which I guess I won't write all the name for now. And then finally, I'll talk about R invariants. And these are going to be for annular links. And then if we have time at the end, I'll tell you about why I'm talking about annular links so much. Okay, so to start with the constructions, those of you who are experts in Pavano homology, you'll have to bear with me, but I know that you might work in something a little bit different. So here's the point of view I'm taking. So first of all, what I like to think about nowadays is just that Pavano homology, which I will abbreviate as KH, is a TQFT. So it's going to take one-dimensional objects, and also if you want a morphism, you're going to have an additional sort of time dimension talking about how you're changing a one-dimensional object via a cobordism. So the 1+1 cobordisms to, and we'll just say F vector spaces. It's actually more general than this, but let's just say F is a field for now to make everything easier. So you really have a two-dimensional Frobenius algebra. And in this case, it's going to be this two-dimensional Frobenius algebra. And for objects, you're going to assign nothing as a one-dimensional manifold to just a copy of the field. If you have a single circle, I'm doing closed one manifold, so we're going to have circles. You're going to assign this algebra A. And then, of course, if you have more circles, you just tensor these algebras together. So a bunch of circles, you take to n tensor copies of A. So this gives you 4 pictures that you can put together. So if you want to talk about the cobordisms or the morphisms in this under this TQFT, you basically have things like the inclusion of F into A, which tells you that a circle has been born. I'm moving left to right. Of course, you can have 2 circles merging. You can have, oh, this is called multiplication. So A tensor A goes to A. The opposite of that is going to be one circle splitting into 2. And then the opposite of birth of a circle is just a map from your algebra to your base field. And this is really all you need. So from this, you can then use this to define a chain complex, which is actually going to define Pavano homology. So roughly, you should start with the idea that you need to use this information to categorify the Jones polynomial. In other words, you should be able to get some sort of grading so that if you track that grading using a variable, you'll be able to extract the Jones polynomial from this homological object. So just as an example to keep in mind, if you want to build the invariant, let's just say you start with this picture of a hop link. What you're going to say is that, well, I have 2 different ways of resolving a crossing. And then I named them 0 and 1. So I can form a cube of complete resolutions, and those are going to be the objects in my 1+1 cobordism category. So if I completely smooth out the above picture using the 0 resolutions, I'll end up with 2 circles. This is 0, 0, 1, 0, 0, 1, and 1, 1. Okay, and feel free to ask me questions. I'm sort of talking in very broad strokes, so a single question might clarify a lot. Okay, so how do I build? So these are just vector spaces, right? This is somehow supposed to be taken to a 2-dimensional vector space tensored with itself twice. This is just 2-dimensional, 2-dimensional, and then 4-dimensional. But I'm going to assign maps to the edges. So notice that just from 0, 0 to 1, 1 to 1, 0, I'm going to have a cobordism that takes 2 circles and merges them together. So I'm just going to use the maps that I talked about above. So these maps above, I haven't told you exactly what they are, but the point is that you can figure out from here exactly what it is. You know how to multiply polynomials. Okay, so that's a merge. This is a merge, so I'm also multiplying. On the other 2 edges, I'm actually doing a co-multiplication because my single circle is splitting into 2 circles. So far, I haven't really done anything other than labeled these pictures. Then by following the rules of what these m's and deltas mean, I can basically write down some linear maps according to the rules here. And then I will collapse them. So it turns out these vertical bars mean constant homological grading. And then there's going to be another grading coming from the fact that you really have ones and x's. So x's can be in a different quantum grading from 1. And then so you get a bigraded theory, but we'll worry about that later. So after you collapse these, you're basically saying that, well, I have a vector space up here and a vector space over here. I'll just direct sum them. And you end up with a complex. So I think this might be the homological degree 0 part, homological degree 1, homological degree 2. It's actually co-homological theory. And then compute the homology and you get Pavano homology. Okay. So I kind of didn't talk about the fact that you maybe the faces actually commute, so you might want to add some signs depending on how you want to compute your homology. But the point here is that this guy, this whole complex is bigraded. There's the homological grading. And then there's the quantum grading, which allows you to extract this extra information, which gives you the Jones polynomial back. Okay. So let's talk about the connections between this and the Heegard-Floer theories. I'm not going to mention too many of them. In fact, I just want to focus on a single one for now, and that's actually the first one. By the way, Heegard-Floer theories originate from Oshvat and Szabó, though since then a lot of people have worked on this. And I should also say that Pavano homology was defined by Pavano in 2000. So typically the relationship you'll see is that Pavano homology of a knot is going to be somehow the beginning of a spectral sequence, and then you do some other stuff and you end up with some Floer theory. So you typically see something like this. There are, of course, many variations on Pavano homology at this point, but you should typically expect to see something like this. So one example, which is very relevant today, also by Oshvat-Szabó, a lot of people had started to notice that this might be the case, but they wrote this down. If you take the reduced Pavano homology, that just means it's just a little bit smaller. You just add a base point. There's a spectral sequence from here to the simplest version of Heegard-Floer homology, and this is a 3-manifold invariant. So it actually goes to the double branch cover of the knot of S3. Remember, the knot is always going to be living in S3. Okay, so from here, I will refer back to the spectral sequence a lot, but right now I have to sort of motivate why we're sort of doing things similar to this spectral sequence. So I'm going to hop on over to a different construction. Are there any questions about what I've said so far? Okay. So I know I gave a different title when I was giving you the outline of the talk, but this section is going to be about symplectic Pavano homology, and then Szabó's geometric spectral sequence, and then the perturbation. So Seidel and Smith an object called symplectic Pavano homology. And this is actually, I believe it's singly graded, although many experts might know if there's any other information here. Basically, you sort of combine the homological and quantum gradings. And then Abu Zaid and Smith were able to verify a conjecture that symplectic Pavano homology is actually isomorphic to regular, what I call combinatorial Pavano homology, but their proof works over characteristic 0, so it's sort of not known for other characteristics at the moment. Okay, so this is supposed to be the geometric counterpart, and there are many reasons to think that this is sort of a really good way to think about Pavano homology if you want to think geometrically. So here is the rough construction. The point of showing you this construction is to show you that even though Pavano homology, the way that I've shown you previously, is very combinatorial, you don't see any sort of actions of topological groups. From this more geometric setup, you'll be able to see that there's an O2 action, which motivates, when you go back to the combinatorial side, what you should combine, what things you should define. So here's the brief construction. There are multiple ways of thinking about this. I'm going to be following actually I would say I was reading a paper by Hendricks, Lifshitz, and Sarkar, who was writing down what Chifre and Menelescu had interpreted from Seidel-Smith's paper. So I'm going to draw pictures from basically that point of view. Oops. I don't speak or write French, so I apologize if my accents are going the wrong way. So instead of starting with just any old diagram, you're going to start with a bridge diagram. What that really means is just that you have just some red arcs and some blue arcs, but somehow the red arcs themselves don't cross over themselves and the blue arcs themselves don't cross over themselves. So for example, I can start off with, I'm going to try to draw a trefoil. I think I learned to draw this picture from Kristen. Okay, so in this picture, you see that there are going to be 2 red arcs, 2 blue arcs, and of course, to connect them, there are a total of 4 points where the red and blue arcs meet. So from this information, you can actually think about my picture here as living inside a copy of the complex plane. So then these 4 points are going to give you points P1, P2, all the way up to P2n. Okay, so now we're going to pass to something slightly bigger because we need to think about what lies over the arcs in a higher geometric space. So you're going to define an affine, algebraic surface S inside C3. So there's going to be a Z, U, and V copies of C, defined by basically you want U squared and V squared, which is going to sort of give you the equation of a circle to evaluate to like negative P of Z. So what's really happening here is that if I label my red arcs by A, I, and I label my blue arcs by BI, I can then in this bigger space see that it's supposed to be some sort of topologically an S2, right? It's going to be an S2 that's sort of pinched off on 2 points where it starts meeting the blue curves or the blue S2s. So sigma AI, which lies above the red curve inside S, is topologically an S2. Similarly, above BI lies a different S2. And so from here, you can just see something that might look like this, right? You'll see some points, and let's say that AI lies in this copy of C, just C, and this is PJ and PK. Then above here, in my complex three-dimensional space, I have this bubble. And if you look at the way that this was defined, well, you can see that there's an O2 action because you really do have just this circle up in here. You could rotate the circle, right? You can rotate this entire bubble. That gives you an S1 action. Maybe I shouldn't try to draw it. You can totally see what's going on. So there's an S1 action, and then there's also a reflection action. And these two combine to an O2 action. Okay. So from here, what happens is that you want to kind of do a Lagrangian intersection floor theory. So you're going to just pass to the Hilbert scheme, and then you basically just take the red arcs, you have these sigma AIs, multiply them together to get your Lagrangian for the red stuff, and then you get a Lagrangian for the blue arcs, and then you have to figure out some transversality issues, and then you will get symplectic Pavano homology. So I'm going to very briefly write that down and just say you're going to pass to the Hilbert scheme, and then there's going to be some Floor theory. There's going to be some subset of inside here, and then there's going to be two Lagrangians corresponding to the arcs. Okay, so now what I'm really interested in is looking at what happens under localization in very big air quotes. So if you want to hear more about the localization results under this actual action, you should read a paper by Hendricks, Lipschitz, and Sarkar called A Flexible Construction for Floor Theories, I think. The keywords are flexible construction. But let's just think about it without actually computing the math, just thinking about what could happen if everything worked out perfectly. So let's recall a typical classical localization theorem would look something like this. So I would have maybe Z mod P acting on a space X, and then from this I get a spectral sequence relating some homology theory of X over FP with the same homology theory. In this case, it's singular cohomology for the fixed point set. Okay, so for floor theories, Seidel-Smith had a different paper, which basically handles involutions for some floor theories. So they give some conditions for when the localization does work. Sometimes it doesn't. But of course, they have shown that for symplectic Pavano homology, you have like a periodicity and you're not, then you do have this sort of localization. But let's first think about what happens if we pretend that Seidel-Smith's spectral sequence totally works here. If Z2 is acting on my my symplectic manifold, and then these two Lagrangians, right? So we really want to say that we're flipping one of the coordinates, and let's just say we're flipping the V coordinate. Then the fixed point set would basically just be like a circle, right? So for each sphere that is lying above a red arc, let's say, you're going to have basically just like a copy of S1 pinched off on the two ends at the PIs. So instead of trying to write that down precisely, I'm just going to draw a picture. So previously we had a picture like this. Now all we see after reflecting is that the fixed point sets should sort of be like one of these. Okay, of course this gets fed into like a direct product of a lot of things, but if you think about it hard enough and you're familiar with Heegard-Floer homology, you'll sort of realize that this will now correspond to a diagram for Heegard-Floer homology, because Heegard-Floer homology also sort of looks at, well, you have red arcs, which then when you direct product together in the symmetric product, you get tori, Lagrangian tori. You also have the blue arcs, which when you look in the symmetric product, they give you a totally real torus there. So from this sort of analysis, you actually see that you obtain a diagram, just looking at the fixed point sets under this action, for the Heegard-Floer homology of the double branched cover. And let's say we're working with a knot for now. So assuming that Seidel-Smith's spectral sequence works for this, I don't even know if I have to assume that. But anyways, so we can conjecture that the spectral sequence for the Z2 action on symplectic Pavano homology is going to be the same as the spectral sequence that takes Pavano homology to the Heegard-Floer homology of the double branch cover, which I talked about previously. That's the one by Untitled Chapter. But of course, there's also this other spectral sequence. So what we're thinking about here is that this spectral sequence could be isomorphic to, sorry, excuse me. Could be isomorphic to the Untitled-Szabó Pavano homology to Heegard-Floer homology of the double branch cover spectral sequence. But then there's a third one called Szabó's geometric spectral sequence. Sorry, my allergies are acting up these days. Okay, so Szabó's geometric spectral sequence, which is a very combinatorial theory that he's basically built from looking at this spectral sequence, but it's still conjectured to be, only conjectured to be isomorphic. So these are all question marks. We'll study this in a couple minutes. Okay, so now let's think about the other action. So the other thing is even harder to convince ourselves that there's a localization spectral sequence for, but certainly other people have looked at subgroups, discrete subgroups of S1. So let's think about what happens, like if we really want some spectral sequence that goes to the Lagrangian-Floer homology of the fixed points, then you would want to say, like, first of all, what are the fixed points under this S1 action? So again, remember we had this bubble. If we rotate this entire banana, then the fixed points are going to be right here. And that's all we're going to have. So the fixed point set is going to be basically just these pi. And you can very, very quickly convince yourself that if you had two Lagrangians, so Ka, they're fixed points, and these fixed points, these are both going to be sort of copies of S0. But the thing is that these S0s kind of correspond to what are the ends of my arcs. So this might be something like a pair Pi, Pj, and then this might be a pair PR, PS, or something like this. And if you think about it this way and really keep track of everything, it will, in like less than 5 minutes, be clear that if you take these very discrete sets and you intersect them, the size is going to be 2 to the L, where L here is the number of link components of your diagram of your link. And this is purely because of just the combinatorial, like you just compute and you'll see it. Okay, so if you're familiar with Pavano homology, you'll really note that there's sometimes a complicated theory, and then there's oftentimes you'll have a situation where you do some flavor of Pavano homology and you end up with just 2 to the L dimensional something. So 2 to the L, only depending on the number of link components, comes up a lot. And one of the most famous ones is Lie homology. But today I'm going to work over F2. So I'm actually going to talk about a more, a second type, which we now call Barnaton homology. So this is basically, you've added differentials and now the whole thing is collapsed to something very simple. Okay, so now if we look back, we see that the geometric version of Pavano homology, which is symplectic Pavano homology, has this circle action and this reflection action, and their fixed point sets, well, they're in quotes localization spectral sequence, remind us of, first of all, the spectral sequence from Pavano homology to the double branch cover, the Higard-Filler homology of the double branch cover of that knot. And second of all, the other part of the action just localizes potentially to something that is 2 to the L dimensional. So if we take this intuition back to the combinatorial side, we could think about, well, if we take away the geometry and just work with concrete chain complexes, what should we expect? So this brings us to Sarkar-Seed-Szabó's perturbation. So this is a perturbation of Szabó's geometric spectral sequence. So you really want to combine Szabó's geometric spectral sequence with ideas behind Barnaton homology. One way to think about Barnaton homology is that you're changing your Frobenius algebra, but another way is to just say you have your original theory and you just add some differentials. So I'm going to actually talk about the filter version that is relevant to what Lynn and I did right now, just because it'll just be more useful for the rest of the talk. But keep in mind that this is actually going to be a theory over like the cohomology of BO2, right? So it's like a much bigger complex. So I'm going to have a complex with chains. I'll denote it as chains filtered total for now, and then there's a filtered total differential. These chains are going to be the same as those for Pavano homology. So like I showed you at the very beginning, you basically just say, if you have a circle, you attach a 2-dimensional vector space. And then if you have multiple circles, you just tensor that by itself a lot of times. This is actually going to be something quite extensive. Okay, so I'm going to call this Pavano homology plus H1. So if I'm thinking about Barnaton homology as the same chains as Pavano homology, but with extra differentials, then H1 is going to be my perturbation. So what we have for the filter complex is basically D1, which is just exactly equal to the original Pavano differential coming from the Frobenius algebra. All the D's together are the differentials from Szabó's geometric spectral sequence. H1 is this guy right here. It's the Barnaton deformation. And then these HIs above H1 are going to be differentials that have the same flavor as Barnaton's deformation. So the index is going to be the homological degree. Same thing on the D side. So this spectral sequence, of course, is going to have longer differentials in the homological direction because you're supposed to sort of collapse Pavano homology down to something smaller, which is going to be the Hager-Floer homology of the double branch cover. So HIs are similar to H1. Okay, and just, I know that if you haven't seen this before, it's kind of just weird. So let's just quickly give an example of what this might look like. So previously we had a Hopf-link picture. Let's see, I'll just draw it really quickly. Previously we had differentials like this. Now there's going to be a rule in Szabó's geometric spectral sequence that there's also going to be potentially differentials this way. And so this is something in D2. And it turns out if you ever see a picture that looks like this guy, and then there are also actually decorations in Szabó's geometric spectral sequence, sort of corresponding to like how you perturb something to be able to compute your, usually would be like a Floer theory. Then you would also have a map from 1 tensor 1 here to 1 tensor 1 at the end of this edge, or this facet really. So from the Hopf-link example, you see that you actually do add differentials. All right, so that is the conclusion of the second part, or yeah, the second part where I'm telling you about Sarkar-Seed-Szabó's perturbation. Are there any questions about this? Okay. Here is the third part where I tell you about these filtration defined invariants. So if you look up here, you know that for example, for the homological grading, which were these vertical lines, this complex is not really homologically graded because D2 somehow shifts your homological, it has homological degree 2, whereas these edges only have degree 1. But you do know that it doesn't ever decrease homological grading. So you have a filtered complex. Okay, so Rasmussen's S invariant is basically defined using this sort of idea. So I'm not going to actually write down absolutely everything, but here is one way to write down the S invariant. Basically what happens is if you use a slightly different Frobenius algebra, oh, sorry, we don't need the T. So by work of Unsuli, she just perturbed, just like the Barnaton perturbation, but she perturbed over a characteristic 0, the original Pavano complex. So you have Q adjoint X and then X squared minus 1. If you stare at this for a while, you can figure out exactly how to multiply, how to co-multiply. And what you end up with is that the Lie homology of any link is just going to be 2 to the L dimensional. And again, L is the number of components of L. But that means that there are these canonical generators at the end. So if you want to think about this as like towers, you could just add another variable here and think about it as like you're left with just 2 to the L towers, and you basically want to say, what is the quantum grading of the thing at the bottom of the tower? And that's going to be your Rasmussen S invariant. But one way I can talk about this is that this is for a knot generated by 2 things. There's 2 homological classes, and she actually gives explicit definitions of cycle representations of these 2 surviving homological classes. And these O's and O bars are just the two orientations of a knot. So S is going to be the quantum grading of either of these guys plus 1. So it's not immediately obvious that these 2 things are sort of have the same quantum grading at the end of the day. But roughly the idea is that okay, without getting into details, there's going to be some class, right? And it has a homology class. You can just ask for what is the highest filtration, quantum filtration, in which some representative of this class is still alive. Okay. So this has been very important. This S invariant has been super useful. Just the 3 off the top of my head. First of all, it's a slice genus bound. So this allowed for another proof of the topological Milnor conjecture. This was in Rasmussen's paper. Originally, it was proven by Kronheimer and Ruvka using gauge theory. You can also port this idea to contact topology. So Lenny Ng proved that you can get a Lagrangian Thurston-Bennigan bound using the S invariant. And most recently, Lisa Piccirillo proved that the Conway knot is not slice, and that was sort of a very open conjecture for a while. Okay. But we can take this idea and apply it to more general Pavano type theories, right? So anytime you have a filtered complex, and then you have a spectral sequence where this thing goes to something quite trivial, you can then trace it back and say, where does the surviving class lie? Like which filtration level does it lie in? So I'm going to take the point of view of filtration gratings instead of towers, but you can of course think about these as towers if you'd like to. Let's move into the territory of annular links. So Asaida, Pshititsky, and Shikora, and I should also add here, probably also Lawrence Roberts. Basically, they showed that the Khavanov-Lie complex, if you're talking about a link that lives in an annulus cross I, so a solid torus, or you think about it as S3 with a distinguished unknot acting as some sort of axis. So for a link inside annulus cross I, the complex admits another grading. And this grading is what is now known as the K grading. Roughly what this does is, if you look at your generators, so again, we have this Hopf link picture. Somewhere up here is a cashew, somewhere down here is another cashew. But over here, we have 2 circles. If we thought about the original picture as having a distinguished point in the picture, so there's some sort of, the Hopf link is sort of wound around some axis, then we can carry this axis through all of our generators in our cube. And it looks like these guys might have some non-trivial interaction with this axis because it separates 0 from infinity. Whereas all of the other circles don't really have any winding number around this axis. So that's basically what the K grading is. It's like a winding number grading. So then Grigsby, Licata, and Verley defined a Rasmussen-like invariant, but more general. So they said that, let's say I have an annular link. I can define dt just like Rasmussen defined S, except that now my filtration grading, well, I'm going to have a one-parameter family of them. So for any t inside the interval 0 to 2, I can define not just the quantum grading, but I can mix my quantum grading with this annular grading. And then for each of these, if I specify t, I get a grading. Then I look at the surviving Lie generator. I will get an annular Rasmussen invariant called dt. So this is modeled after Upsilon in Hager-Floer homology, where Oshvat, Stipchitz, and Szabó mixed the Maslov and Alexander gradings. And that generalizes tau, which is sort of the concordance invariant from Hager-Floer homology. Okay. So this brings us to what Lynn and I were doing with the Sarkar-Seed-Szabó perturbation. So originally in Sarkar-Seed-Szabó's paper, they already had these longer homological degree differentials coming from Szabó's spectral sequence. And they also had these longer Barnaton differentials in the homological direction. And of course, both of these are quantumly filtered. So they already had two different filtrations, which means that they were able to mix those two filtrations together to make an Upsilon type invariant. So Sarkar-Seed and Szabó had defined SU invariants. So Lynn and I showed that their theory is functorial, and therefore these are actually, these end up being annular, or sorry, just concordance invariants as well. So we then realized that there is actually a way to look at the annular version of this as well. So if you look at all of these infinite number of possible differentials, there is still a filtration if you have an annular axis involved. So it's somehow, it's not annularly graded, of course, but it does give you a filtration. So here's our main technical lemma. So what I defined above as C filtered total and del filtered total, it's filtered by these three things: homological grading, quantum grading, and quantum minus annular grading. This annular grading is defined exactly the same way as Asaida, Shatitsky, Shikora, Lawrence Roberts, Grigsby, Licata, Verley. And then we can, of course, define S sub RT to be the grading of, and in this case, we also have canonical generators, but we're not in Lie theory, so I'm going to write it slightly differently. Just generator associated to an orientation. This is for knots. You can, of course, try to define this for a link, but then you have too many canonical generators. You have to specify an orientation if you're talking about a link. What else was I going to say here? Okay, so this means that this is a two-parameter family of annular concordance invariants. Namely, R and T can be in the interval 0 to 1, but somehow this square collapses one of the directions, and you sort of, by the way that we defined this grading over here, you actually have just like a 2 simplex worth of invariance. And so in the last couple minutes, I want to tell you about some properties of this invariant, as well as then potential applications of this invariant. So many of these are shared with Grigsby-Licata-Verley DT from annular Lie, Pavano-Lie theory, mostly because their construction is so similar. So some of the precise details won't be the same, but you should basically think of these as two types of the same construction, but for different characteristics. Okay, so first of all, it generalizes SU. Obviously DT doesn't, but it generalizes S in that case. It behaves sort of well under cobordisms. You can get some bounds. I'm sort of thinking about whether I really want to write all this down, but I've started. So if you have an oriented link and then there's a cobordism to a different oriented link, you can sort of bound how this Rasmussen invariant changes. And it depends on R and T. So the number of annular maxes and mins minus the number of annular saddles plus the number of non-trivial. So those are these maxes and mins that end up being punctured by the axis. Times 1 minus t. Okay, so this is just to show you that there's some way to control how this invariant changes. This is actually also piecewise linear in any given direction. And this is simply because of the way it was defined. So if you have only a finite number of generators, then as you sort of change your grading by tilting the plane that you want to compare your gradings of your generators to, since there are only finitely many points where things can change, you're just going to sort of have a line until something changes. So this is not like hard to prove, but it's interesting because so Gage Martin very recently basically said, okay, so if dt, which is the Grigsby-Licata-Verley invariant, can only change at a couple of points, well, we can maybe think about what kinds of shapes dt can take on. So she used dt to compute Rasmussen's S invariant for all 3 braids, or 3 braid closures, I should say. So this is really cool because basically what she says is that if you have a 3 braid, there are only a very small number of possible shapes that dt can take on as a function of t. And from there, you can use classification of 3 braids to say, okay, then these braids must be this shape, and therefore I can figure out what S is. So we haven't done this for this theory, but the fact that it's piecewise linear in any given direction means that one could potentially also say if this is some sort of polytope or if it's some sort of simple looking shape, you can just say if I have a restricted class of knots, let's try to figure out what S is or something more general than that. Okay, moving into the world of transverse links. So what I mean by that is in the rotationally symmetric or contactomorphically the standard contact structure of S3, you can get an S-Benniken bound. But since we're working over F2 in this theory, you actually get an F2 bound. Sorry, this is a name. So just as a side note, S over F2 is not the same as S over Q, which is why I'm specifying this. But basically the self-linking number of the transverse link that you get from closing a braid beta is going to be less than or equal to the S invariant over F2 minus 1. And you sort of needed this extra bigger version, not just the original Rasmussen invariant, to show this, because you needed this annular nature to prove this. You have to sort of use Plumnevskaya's invariant to think about this. Over characteristic 0, this was already proven by Plumnevskaya and Alexander Shumakovich. In fact, there's also better bounds. You can write this in terms of R. Well, I don't know if it's better, because computing examples is very hard, but one could hope that it would be better, because you have sort of more ranges of possible invariants to compute. Okay, so this guy is related to Sarkar-Seed-Szabó's S upper U invariants that they defined in their original paper. In addition to this, I'm not going to write it down, but just like for Grigsby-Licata-Verley, you get a necessary condition for quasi-positiveness, because it's also related to braid closures, and annular links are basically just a bigger class than braid closures. You get a sufficient condition for right veeringness if you think about braids as a mapping class group of a disk with distinguished points. And then we can also talk about like what happens if you do a tangle composition, because we're talking about things in an annular way. So there are a couple of things I want to mention last of all. So this gives you some information about transverse links, but you could also ask a bit more. So you should definitely look at Grigsby-Licata-Verley for this. The same question that they had, we also have for our invariant, because they're constructed so similarly. The main question is, you might have to think about this a little bit, but remember that transverse links are just annular links mod a positive stabilization. So this is really thinking about the rotationally symmetric contact structure, and then you can positively stabilize because that cobordism follows the, well, that isotopy follows the planes, but you can't do it the other way because that will go through the planes and not preserve transversality. So if the following is true, so this is a positively stabilized version of this braid. So if this thing is true, then you can define a transverse invariant. Which would be really useful, because then you can study like a numerical transverse invariant. The problem is that currently the properties that we've looked at are sort of symmetric between positive and negative stabilizations. It's not to say that we've tried everything. Of course, the Pavano complex isn't really going to behave the same way under positive and negative stabilization, so there's much to think about here. I guess I'm sort of out of time, so I'll write these really briefly. The other thing is we filtered Pavano homology into annular Pavano homology. Right? There's this notion of an annular version of Pavano homology. So one could also ask what happens to the spectral sequence. So if originally we were looking at something that roughly looks like this, if you really squint, maybe there's the spectral sequence after looking at our annular filtration of Szabó's GSS could give us back Lorentz-Rodbridge spectral sequence, which roughly looks like you have the knot-Floer homology of the knot inside its double branch cover. So maybe this would come from the annular filtration on just the GSS portion of our technical lemma. And thirdly, of course, there are questions about just annular concordance. So I won't talk about this too much, but roughly you can think about these things called satellite constructions. And whenever you're doing a satellite construction in knot concordance, you're basically saying, I'm going to tie a donut into the shape of a knot, and the donut itself contains an annular knot inside it. And this is an operation which we don't know very much about. And so we need annular concordance invariants to study those. Okay, so I'm going to stop there for any questions.
Great, thanks so much for the great talk. Let's give Melissa a round of applause.
Thank you.
Great. Are there any questions for the speaker? Let's see, I had a question, actually. I'll paste it in the chat too. In the beginning of your talk, you had an interpretation of this map from Pavano symplectic to the combinatorial map, and I was wondering how you can match up, if you know how you match up the Lagrangians with the picture that you drew. Hopefully that makes sense as a question.
Oh, I'm sure it does, but I feel like there are probably people here with, okay, Mohammed is here, and he definitely knows how to do this, so I'd be happy if he could answer.
I could answer, so the first thing you do is you take cross-seamless matchings, and you assign to, there are some finite number of them in each dimension, Kaplan number. You assign to each one of them a product of Lagrangian, a copy, basically collect a Lagrangian in some Hilbert scheme that's a product of S2s. And then the next thing you have to prove is that the braid group acts. And so you take one of these things, you apply the braid group, which gives some symplectomorphism, a generalization of this symplectic Dane twist, and then that's how you do it. So, but you want to think at least the way that's simplest for me to think is in terms of some basic Lagrangians and then action of a braid group.
Okay. Very cool.
Thanks, Mohammed.
Are there any other questions for the speaker?
And of course, if there are no questions, I'm also happy to hear what this reminds you of and like what parts of this are related to your work or like interesting from your point of view later on.
Let's see. Maybe would you mind explaining this bridge diagram again at the start that you drew?
Oh, yeah. This one here?
Yeah.
Oh, yeah. Well, right. So it's basically just, you can think of like the red arcs as, so if you, depending on your point of view, the way that I think about it is the Earth is like lava covered in a layer of water, right?
Okay.
So like the blue is like a snake that lives in the water, and the red is a snake that lives in the lava. And then they kind of touch, well, multiple snakes. They kind of touch at the Earth's crust at the black point. So imagine the red like really going down under the blues, and then the blues kind of being above the reds. And then you see that this is actually going to be a diagram of the trefoil, even though I failed to draw the crossings in.
I see. That's very illustrative.
Although I might have messed up the conventions compared to other people's conventions.
So, and then you're assigning this sigma, these S2s based on that diagram. is your map?
Yeah, so you're thinking of this C as like CZ, and then there's also like another 2 complex dimensions above it. And sort of above each point in either your blue or red arcs, there's going to be a circle because you have u squared plus v squared equals negative p of z. And so when you put all those circles together, you get like a tube along each of these arcs, and the circles collapse at the endpoints pi.
Oh, okay. I see. That's like the picture you drew down below.
Oh yeah, yeah. So this is like a
Okay.
fiber. Well, not a fiber. This banana is lying above an arc.
Very cool. All right. Let's see if there are no further questions for the speaker, let's give Melissa a round of applause again.
Thanks for coming.
Thanks for speaking. Let's see if anyone stays around. Sometimes people stick around for a discussion afterwards.